So let's try and name this 3 carbon atoms. So that's prop. And aldehyde. So that's the most important functional group. It would be aldehyde, and it's going to be dial. Okay? I mean, there are 2 aldehydes. For an aldehyde, you don't really need to write the position, but you can, even if you write it, nothing wrong with it. Okay? It's always at the end. And there's an OH. I mean, the OH is less important compared to an aldehyde. Okay? There was a precedence thing. क्या था वो precedence that you have carboxylic acid and aldehydes are much more important than alcohols. So if you're not naming the molecule based on an alcohol, the alcohol group changes into a branch. It changes into hydroxy. So the other thing would be for this molecule would be that it would be 2-hydroxy. Okay, there's an OH group. So before this thing, this would be 2-hydroxy propan 1,3-diol. So that's the name of the molecule. Okay, is this clear? Abha, is this clear? Rida, Hiba, is this clear?
Yes, sir.
Achha, so, and I'm just going to repeat the molecule that was done yesterday as well. That this one over here, it's a straight chain, 1, 2, 3, 4, 5, and 6 carbon atoms. So that's hex. Okay, you start off with hex. Okay, that's the main chain. I mean, there is only one chain. So that's hex. And it's a carboxylic acid. So carboxylic acid is definitely oic acid. That's the most important group. Okay? So you named it after carboxylic acid. But it has a ketone as well. And I told you a ketone remains a suffix, so it would be on as well. And the ketone, you're going to start counting from the most important group 1, 2, 3, 4. This would be 5, and this would be 6. So the ketone has a position number 3. So it would be hex 3 on and oic acid. And so it's hex 3 on oic acid. Now the rest are all branches. So there is chlorine, another chlorine, and an NH2. NH2, if it's a branch, it would be called amino. This is
Sir,
chloro.
shouldn't be an N over here, hex N, because there's a double bond over there.
Acha, haan, sorry. AN, I missed the AN part. Okay, AN or EN, it would be, it's going to be EN. And the double bond is at position number 4. Okay, you see that we had missed the AN and EN thing. वो mention ही नहीं किया. And now we move to the branches. So it's going to be chloro, chloro, and amino. Amino alphabetically is first. So branches would be alphabetical, and it would be dichloro because there are 2 chlorines. But you have to mention the position of each chlorine separately. So the amino is at position number 2, and the 2 chlorines are at, one is at position number 4, and the other one is at position number 5. So that's going to be, I mean, these are your branches. This over here is your main chain. You have to put them all together. So you get your molecule. Okay. Clear? Is this clear to everyone? Abha, is this clear? Rida, Hiba? Bazga, आपने तो मेरे ख्याल से यही, रिदा आपने भी यही किया था, बस वो I think the only mistake was कि alphabetical. ठीक है. So now we're going to move to the next thing, which is isomers. Okay, we're going to start talking about isomers, and beach mein we're going to keep on revising this skeletal thing and this naming thing. So isomers. And isomers, first thing is the definition of what an isomer is. Isomer is you have the same molecular formula. And I mean, I mean, let me write this complete statement. It's molecules having the same molecular formula. So molecules that have the same molecular formula, but they have different structural formulas. structural formulas. Okay, you've done this in O levels as well. Same molecular formula, different structural formula. The first thing is, why do you even study isomers in the first place? One example of an isomer would be that I have C4H8. This could be 4 carbon atoms in a row, and the double bond is over here, and there are 2 hydrogens. One hydrogen, this would have 2 hydrogens and 2 hydrogens. And there could be other versions of the same molecule. That the double bond could be on the second carbon atom over here, and and this could be an isomer because it has a different structure. Or there could be another version of the molecule. It's going to have the same molecular formula, but it's going to have a different structure. So it could be 3 carbon atoms in a row, and there could be a carbon atom coming out as a branch. This is still C4H8. So that pretty much sums up. That pretty much sums up all the 3 isomers. But remember, these are structural isomers. Okay? There's another type of isomers that we're going to study. But right now, I'm talking about structural isomers. Okay? So structural isomers, and let me even mention it over here. Okay, what's a structural isomer? Okay, they're going to have atoms are going to be connected differently. Atoms, groups are going to be connected differently. Okay, they're going to have different connections, and that's what's happening over here. So these are isomers. These are structural isomers. Now, one thing about this is that the first very important thing is, why do you even study isomers? I mean, what's the point of learning that C4H8 can be represented in 3 different ways? What actually happens is, when you're doing analytical chemistry, especially when you're trying to figure out, for example, you have a coronavirus, right? And there's a specific molecule that it emits. So, I mean, the very first thing is, you always figure out the formula of the thing. You figure out how many carbon atoms there are, how many hydrogen atoms. That's the first information that you get when you're trying to analyze. Okay? Because I mean, these formulas are never, I mean, in nature, they're not written over there. Okay? You have to use analytical techniques to figure this out. Then you figure out, the next step would be, okay, like a scientist, if he's trying to figure out a particular molecule, the first thing usually is that you get the molecular formula. Then you try and figure out how many different arrangements are possible. Then you try and investigate that how could you distinguish between all these molecules, and which tests should you perform so that you could distinguish whether it's this molecule, or whether it's this molecule, whether it's this molecule. So most analytical techniques, they depend a lot on your and on the ability to actually create these isomers. So so most of the time, the information that you have about a molecule is very, very incomplete. The picture is very incomplete, and you're trying to do a guessing game whether it's this one, or this one. Okay? So, which is why isomers are very important when it comes to analytical chemistry, when you're trying to figure out, decode what a molecule actually looks like. But anyways, I'm going to talk about 3 different. Is this clear? Structural isomers. Is this clear to everyone? Baza, clear? Rida, Hibab?
Yes, sir.
Okay, Abba, is this clear?
Yes.
The next thing is, there are different types. Right now we're just doing O levels. Okay? Now the next thing is, there are different types of structural isomers. The first one is they're called chain or branch isomers. Okay, that's the first thing. Number 1. Now there are types of structural isomers. So types of structural isomers, chain and branch isomers. That's the first one. What you simply do in a chain or branch isomer is, that you change the carbon branches. So if you have 4 carbon atoms in a line, then an isomer of this molecule could be C4H10. This is C4H10. So an isomer of this molecule could be that you can have 3 carbon atoms in a line and the 4th carbon atom could be a branch. So you change the carbon branches. Now that's the first type of isomer. I mean, the 3 things that you could do. Change the carbon chain. So they're clearly different structures, but they have the same molecular formula. The second thing that you could do is, okay, you can change, I mean, they're called positional isomers. Positional isomers are, like I have an alcohol. Okay, this is propanol. And these are my hydrogen atoms. So the second thing that I can do is to change, to get a different formula, a different structural formula is that the OH is attached. I'm not going to change the carbon chain. Okay? If I change the carbon chain, then it's going to be called branch isomers. The other thing that I can do is the OH is attached at the end. I'm going to attach it at position number 2 now. Okay? So that's a positional isomer. Number 3. Number 3 would be called functional group isomer. So there is in reality there is no limitation. You can do whatever you like, as long as you come up with a valid structure, as long as the number of atoms are still the same and the structure makes sense. Um, so the next one is functional group isomer. Functional group isomer is, okay, you're going to have like ketone and aldehydes. This one is an aldehyde. Okay, the double bond O is right at the end. Now what I can do is I can if I bring the double bond O in the middle, then it's a ketone. So this one, I said this one is an aldehyde, this one is a ketone. So you can have different functional groups, uh, and they can still be isomers. Carboxylic acid and alcohols and esters. Like you have a carboxylic acid. Actually, we haven't done esters in naming yet. So this is a carboxylic acid, and you can have an ester, which is, if you remember, it's this thing. Both of these have the same molecular formula, but they obviously have drastically different functional group. This one is a carboxylic acid, whereas this one is an ester. Because one of them is an ester, the other one is a carboxylic acid. So many functional groups can be isomers of each other. Uh, you can have so you can have let's talk about this one. Like let me try. Well, that's multiple functional groups, but many functional groups can be isomers of each other. One example is like you have an alkene. Alkene and cyclic alkanes can be isomers of each other. I mean, there would be different functional groups. The first one is C4H8. This one is also C4H8. One is an alkane. The other one is an alkene. So both of them are isomers of each other. So that's your 3 types of isomers: positional isomers, chain isomers, and functional group isomers. Although you don't need to stick to them, but a lot of questions specifically ask for a specific type of isomer. Okay, so if you're given this molecule, you're talking about branch isomers, just change the carbon chain. Okay, arrangement. Remember, bent rotated versions are not isomers. Like if you start drawing this thing, like this one over here. If you start drawing this thing, this is definitely not an isomer. You've just bent the first molecule up. As for example, this molecule is not an isomer of this molecule over here. Okay, I was talking about this molecule. These two are exactly the same. So just remember bent, rotated. I'm going to write this down as well. Okay, let me get this up first. Okay, this is not an isomer. ठीक है ये clear साहब बाजार is this clear Rida Heba Aba is this clear Minahil
Clear, sir.
Minahil clear है Aba clear है is this clear
Yes, sir.
अच्छा so the three types. So I'm just going to do. You have to be very creative. You can come up with many isomers. Okay, so I'm just going to do an example. Okay, just remember. Uh, I mean, this is all O levels. Okay, we're going to quickly switch to A levels just after doing this example. So let's say I have etheric acid. Okay, and I'm being asked to draw isomers of etheric acid, and this is the displayed formula. Now this is C2H4 and O2. Now there probably many ways of changing the structure of etheric acid. Okay? The structure has to be changed. One way is I can switch the position of the OH. The OH is attached to this carbon atom. I can attach it to the other one. So here's one isomer. I'm going to keep double bond O over here. The H and the H and the H over here. Okay? So that's one way. It's the same molecule. But that's actually remember not all isomers can be classified as functional group. I mean because most isomers would be a mixture of the two. Okay, not all of them. Like you can have a chain and a positional isomer at the same time. You can have functional group isomers and positional isomers at the same time. So the classification is not that. I mean you can't like what I did over here. You can probably classify it as a functional group isomer because it was a carboxylic acid, but now it's an alcohol and an aldehyde. So it's kind of like a functional group isomer. Uh, but the classification can get mixed up. What else can I do? What I can do is I have a double bond over here. I can put the O in the middle between the two carbon atoms. So that's what I'm going to do next. So that's again probably a functional group isomer because I've changed the functional group. Now it's an ester. Okay, this is an ester. This thing over here is an ester group. It's again C2H4O2. What else can we do? What I can do is there's a double bond over here. What I can do is I can put the double bond between the two carbon atoms. I can change the position of the double bonds. And that way, this would be OH, this would be OH, and this would be H and H. So that's again an isomer. It's a completely, but there's nothing wrong with the structure, and it's still C2H4O2. The other thing that I can do is I can put the two OHs on the same carbon atom. So that could result in another isomer. So that would be C double bond C and both OH groups. So that's like a positional isomer. I mean, compared to this one. Okay, I've just changed positions. Now, so that's like how many have I drawn? That's like 5. 4 isomers, 5 including this one. So what else can we do? I mean, we're running out of options. We've done pretty much everything. The other thing that I can do is I can go with cyclic structures. Like I can have a structure where there's an oxygen over here and there's a double bond O over here and the two hydrogens over here. But there should be a double bond because I'm running out of hydrogens. So there's probably an OH over here, right? So that's, I mean, there's nothing wrong with the structure that I've drawn. It's C2. There is something wrong with the structure. I mean, this should have one more hydrogen. right? So that's another isomer. Uh, and the structure is perfectly fine. There's nothing wrong with it. All of them are making proper number of bonds. Uh, and we can have, so you can just go on. You can just keep on changing the arrangement, and you can get more and more different structures that are possible. Okay, so that's how structural isomers would be done. Now, is this clear? Minail, is this clear? Abba, Mazga, Ridaiba, is this clear?
Clear, sir.
Yes.
Yes.
Acha, now the other thing is, अच्छा इधर ही मैं लिख देता हूँ. Remember this that structural isomers can have drastically different properties. ठीक है? I mean, this molecule is completely different molecule. It has hydrogen bonding. This one doesn't have hydrogen bonding because it doesn't have O and H together. So the physical properties can be different. The chemical properties can be different. Lots and lots of things can be different when you talk about structural isomers. I mean, they're basically completely different species. So structural isomers, I mean, they absolutely have nothing to do with each other's chemical or physical properties. Uh, so no relation in physical or chemical properties between isomers. And especially if the change is drastic, for example, over here, all of a sudden this was a carboxylic acid, whereas this is an alkene and an alcohol. So the change is pretty drastic. And the change in physical and chemical properties are going to be different as well. So structural isomers, they have absolutely no relationship when it comes to physical and chemical properties. Now the next one is these are called stereoisomers. Stereoisomers. Now, stereoisomers are isomers. I mean, it's the same definition. They have the same molecular formula. Actually, they have the same molecular formula, but just hold on. Sorry. So they have the same molecular formula, but different structural formula. Well, the structure is different. Why? Because of a different three-dimensional arrangement. So a different 3D arrangement, three-dimensional arrangement. So what's basically happening is that the two molecules would look, the connectivity would be exactly the same. ठीक है, same connectivity. Now in the last part, you were changing the connectivity. The molecules were changing drastically. Now what's happening is that the connectivity is even the same. ठीक है, the bond orientation is basically different. If in one molecule the bond is pointing down, in the other molecule the bond would be pointing upwards, but it would be connected to the same atom. So bond orientation is different. So the first one that we're going to do, that's called, I mean, stereoisomers have two versions. Number one is geometric, and number two is called optical. So there are two basically different types of stereoisomers, geometric and optical. So we're going to talk about geometric isomers first. Now, geometric isomers they're also referred to as cis trans. One of the molecule is going to be called cis and the other one would be called trans. The first thing is I'm going to talk about is when do geometric isomers, when does it happen? It happens. The first necessary thing is that the carbon double bond carbon has to be there. And the second thing is that each carbon in C double bond C must be bonded to two different groups. It must be bonded to two different groups. Now there are a few things that have to be that you have to know about double bonds. I've told you previously as well that when there's a double bond, there's a pi bond. Carbon is making three bonds, so three electrons kind of get stretched in different directions. So let's say this is the molecule. Carbon is bonded to three atoms, and they're getting pulled in different directions. And there's a fourth electron, and the fourth electron is not doing anything. It eventually ends up forming a pi electron cloud. So they end up forming pi bonds, right? So there's an electron density overlap above and below the sigma bond that's in the middle. Now, what happens is that when a pi bond is formed, the molecule cannot twist. I mean, if you try to switch the position of the H and the Cl, it's like if you try to pull this H downwards and the Cl upwards, this carbon is not going to rotate. If the double bond wasn't there, the carbon was capable of rotating. Like, I mean, if it was only attached to a sigma bond with electrons in the middle, the carbon over here could rotate. The H could swing around and point in the downward direction. The Cl could go up. But if there's a pi bond, the pi bond has to break. Like this carbon would not rotate. If you try to twist it around, it's not going to rotate. It's like I mean, the molecule is locked in position now. If you try to rotate this side would rotate along with it. Is this point clear? Mirail, is this clear? Abha, is this clear? Basga,
Yes.
Zida, Hiba.
Clear, sir.
Okay. So just compare it with single bonds. If a carbon is single bonded, it's tetrahedral. And let's say there's Br and there's H and there's Cl and let's say there's another Br. Now when it's single bonded, this thing is rotating like a wheel. I mean, this side over here, like a wheel is rotating around. So the bonds are kind of spinning around. Okay, nothing happens to this bond. This carbon is like spinning around, uh, like a fan. Okay, these things are spinning around like a fan. But the bond, there's electrons over here. Nothing happens to it. Okay, it's capable of doing that. The nucleus would stay in position. Even if it's rotating around, even if this thing is spinning around, the nucleus would still be attracted to these electrons. But that's not possible in a double bond. So that double bond is locked in position. And the angles are going to be 120 degrees. All the angles are going to be 120 degrees. It's going to be fan shaped. Now, what that means is that if you look at this molecule, if the Cl is pointing downwards,
Sir, why are angles so important?
नहीं वो तो dipoles depend on angles. ठीक है, so and dipoles determine a lot of properties. So इसलिए the angles are very important. I mean, in this case, the angles are not that important. ठीक है, I'm just writing the angle. Okay, carbon is fan shaped. It's making three bonds, and there's a pi electron cloud above and below the sigma bond in the middle. Achha, so the angle is 120 degrees. Now, what happens over here is that the Cl is pointing downwards. Now, there could be another arrangement of the molecule, and in that arrangement, carbon would be bonded in exactly the same way. It's going to have the same connectivity, except for the fact that the direction of the bonds would be different. Now, if you look at this molecule, the two Cls were pointing downwards in the same direction. But if you look at this molecule, the Cl is still connected to the same carbon atom. Cl is still connected to the same carbon atom, except that the two Cls are now pointing in opposite directions, and you can't do anything about it. Like if the pi bond has formed, then the bonds are locked in position. You can't go about changing the bonds. You can't sort of twist this side, and the Cl cannot point upwards. Okay, so the molecule is going to be locked in position. So is this clear? So what's going to happen is,
Clear.
what's going to happen is that there's going to be a double bond, and each carbon atom in the double bond over here must be bonded to two different groups. Because if they're bonded to the same group, then changing position or whether it's pointing upwards or downwards wouldn't really matter in that case, because they would be exactly the same. If you had an H over here, if what this H pointed upwards, it doesn't really make a difference. Uh, so the groups attached to the double bonded carbon atoms, they must be different. So this side should be different, and these two groups, they must be different. They can be same. I mean, this side could be same as this side, or this side could be different from this side. That doesn't really matter. These two groups have to be different, and these two groups have to be different. Okay, is this clear to everyone? Rida, Eba, is this clear? Abba, is this clear? Bazga, Minahil?
Yeah.
Sir, I
Yes.
have a question.
Yes.
When when the like positions of the H and CO change, did the pi bond break?
You're saying, does the pi bond break, right?
Yeah.
Actually, this molecule is completely different from this molecule. I'm not I'm not changing this molecule into this molecule. Abba, do you get this point?
Oh, okay, okay.
Okay. So when they were formed, like in any reaction, they were formed. This molecule was formed complete. I mean, it's a completely separate molecule. This is a completely separate molecule. Okay. Uh, they have the same connectivity, which is that this carbon is attached to an H and a Cl. This carbon is also attached to an H and a Cl, except that they are pointing in different directions. So the three-dimensional shape of the molecule is kind of different. So it's so remember, these two are not related to each other. I mean, they're completely different things. Having the same, I mean, if you write the structural formula of the molecule, that would also come out to be the same, unless, I mean, this is CHCl, double bond CHCl. Both of them have the same structural formula as well. Unless you draw the three-dimensional formula, the three-dimensional formula is the one that's different for the two molecules. So this is a stereoisomer, and one of them is going to be called a cis version. Cis version is the one which has same groups pointing in the same direction. So that's both the Cls are pointing downwards. So that's your cis, and the trans version is going to be, the second one is your trans version. Okay, let me get this out of the way. So the second one is your trans version. In that case, trans version, the bonds or the same groups or whatever groups that exist in the molecule, they would be pointing in opposite direction. So if you try to name this molecule, the two molecules, it's two carbon atoms. It's an alkene. There's a double bond. So it's ethene and it's dichloroethene. So this one would be called, this one, the top one. Let me go to the top one. So the top one is going to be called cis, and it would be 1,2-dichloroethene. So in front of the name, you're going to write cis. And the second one is going to be called trans, and it's also 1,2-dichloroethene. Exactly same structure, but different three-dimensional arrangement. So this is the first type, geometric isomers, and we're going to search for geometric isomers as long as these conditions are met. For example, if I have a propene molecule, not a propene molecule, let's say a butene molecule. So let's try and find whether butene is going to have, it's going to show cis and trans isomers. So but is 4 carbon atoms, and 2-ene means there's a double bond, and this is CH3, this is H, and this is CH3. So would it form cis and trans isomers? Would it form geometric isomers? Let's look at the conditions needed. You need a double bond. So there is a double bond. Let me highlight it. There's a double bond over here. Okay, so there's a double bond. And the second thing is that each carbon in the double bond must be bonded to two different groups. So if you focus on this carbon atom over here, it is bonded to two different groups. There's a CH3 and there's an H. And if you focus on this other carbon atom over here, it is also bonded to two different groups. One is H and the other one is CH3. So if you draw the three-dimensional arrangement, and you'll be asked to draw the three-dimensional arrangement, you would be asked to draw the cis and trans versions of the molecule. So remember double bond, what you're going to do is double bond, it's going to be fan shaped around the double bond. Okay, this is how every double bond is going to look like. This carbon is bonded to H and CH3. So it would be bonded to H and CH3. This other carbon atom would also be bonded to H and CH3. So which version is this? Which butene is this? Cis or trans?
Cis.
Okay, this one is cis because the same type of groups are pointing in the same direction. So this one is cis butene. And there's going to be another version where one of the side is going to be flipped around. So the other version would be that you're going to have a double bond, same arrangement, fan shaped, trigonal planar around the double bond. And this time, uh, this one has H and CH3, so keep it as it is. The other one also has H and CH3 attached, except that the CH3 would be now pointing in the opposite direction. So it's going to be, this one over here would be trans but to butene. Okay, so cis and trans. So that's how you figure this out. Um, is this clear? Rita, is this clear? Minail?
Clear.
ठीक है.
Yes.
ठीक है. Abhay, any questions?
No, it's clear.
Acha, so remember whenever you have a molecule, let's talk about, let's think of another molecule. I have okay, I have 2-methyl butene. Can anyone tell me whether this would form cis trans isomers? I mean, would it have geometric isomers or not?
Trans.
Nee, would it have geometric isomers or not? I said, remember, this is the structural formula is not the three-dimensional arrangement. Okay? I mean, the structural formula could be made any way you like. I mean, the bonds could point in, they can point upwards, they can point downwards. It doesn't really matter. Okay? So remember, the structural formula doesn't show what type of geometric isomers or what type of stereoisomers it is. I said, but does it meet the conditions? Okay, would it form cis and trans isomers? Kya conditions थी? The conditions were that you need a double bond. ठीक है, that's the first condition.
It won't.
ठीक है, it won't. And the second condition was that both groups on the carbon atom in the double bond must be different. Now over here, this carbon atom is attached to the same type of groups. The other one is attached to different groups. ठीक है, it's attached to different groups, but the condition was that both groups should be different. ठीक है, over here, and this carbon should be bonded to two different groups. So even if you switch the sides, it's going to remain the same molecule. So this would not form. It won't have two versions. It's just going to have a single version. And let's try and do another molecule. If let's talk about propene, and let's talk about 1-chloropropene. So let's try and figure out whether it forms cis and trans isomers, whether it's going to form geometric isomers. So you have carbon, and then there's double bond, there's carbon, and 1-chloropropene. So there's 1 chlorine, and there's H, and there's H, and there's CH3. So can anyone tell me whether it's going to form cis and trans isomers?
It will.
Okay, so the first condition is that there's going to be carbon and carbon double bond. And each carbon in the double bond must be bonded to two different groups. So this is bonded to two different groups. So that condition is met. This carbon is also bonded to one group over here and one CH3 group over here. So that's two different groups. So let me just draw. If you're going to be asked to draw this, तो पहले सबसे पहले the first thing is you have to draw it like fan shape. ठीक है? Just focus on the double bond. This one is attached to an H and a Cl, and the other one is attached to an H and a CH3. And the other version would be double bond, carbon, carbon, etc. The same thing. The first one is attached to an H and a Cl, except this one changed the side. CH3 is pointing downwards. Now it's going to be pointing upwards, and the H would be pointing downwards. That's your other version. Which one is the cis and which one is the trans?
First is cis, the other one is trans.
So you have a cis version and you have a trans version. The H's are pointing in opposite direction. Over here, the H's are pointing in the same direction. Okay. So is this all clear? Geometric isomers.
Yes.
ठीक है हिबा इज दिस क्लियर ठीक है मेरा
Yes.
हेल्प चलो चलिए ठीक है सो लेट्स कंटिन्यू विद दिस इन द नेक्स्ट क्लास देन ठीक है ओके देन टेक केयर
Allah Hafiz.
अल्लाह हाफिज